In this video, I want to talk about the residue theorem. Very useful theorem. In fact, we'll use it, I guess in the next lecture, we'll use it to actually compute some integrals. So here's the main point of this residue theorem. Suppose you have a function f of z with an isolated singularity at some point, say right there. Take a circle around it, radius rho, and assume that there are no other singular points inside. So inside C, f is analytic except at z naught. And the result is that the line integral of f along C is 2 pi I times the residue of f at z naught. And the proof is, well, when you know the existence, we saw last time that there exists a Laurent series. So here's like the analytic part, and here's the part with the negative exponents. And let's imagine integrating each term individually around C. Now for the positive parts, that much is analytic. So the integral around C is 0 by Cauchy's theorem. So this whole part will integrate to 0. Now what about all these terms? Well, in the last video we saw that the integral of dz over z minus z naught to the n is 0 for all n bigger than 1. But when n equals 1, it's 2 pi I. So when you integrate this term, this term, this term, and so on, they'll all be 0. This one will give you b1, and then the integral of dz over z minus c naught will be 2 pi I. So you end up with b1 times 2 pi I. b1 is what we call the residue. Right? It's the coefficient of the z minus c naught to the negative 1 term. So that's the proof. That's sort of the guts of the residue theorem. Now you just sort of put it together. So for the residue theorem, suppose we have a simple closed curve C, a function f of z, which is analytic on C and inside C, except for some finite number of singularities. I don't know, like first, second, third, and so on. Yeah, just some finite number. So draw little circles around each of the singular points, enclosing no other singular points except the point at the center. And draw small paths from C to these circles. So gamma 1, gamma 2, up to gamma k. And then look at this path in red. So this path, you think of it as sort of start like maybe here. And you go part of C, and then you go gamma 1 around C1, backwards on gamma 1, a little more of C, gamma 2, C2, gamma 2 inverse, a little bit more, and then finally at the end, gamma K, CK, gamma K inverse, and we're back to where we started. Well, that path encloses the red. See, that path has been drawn to exclude these singular points, Z1, Z2, and so on, and put them sort of on the outside of the red path. So the inside of the red path has absolutely no singularities whatsoever. So f is analytic inside. So the integral over the red path by Cauchy's theorem is 0. But now think of doing this line integral around the red path. Every one of these gammas, you travel along it twice, once in this direction and once in the reverse direction. So those integrals cancel. Then you're left with the integral along C and the integral around every one of these little circles. But those are taken, if you follow, those are taken clockwise, whereas going around C is counterclockwise. So you end up with the integral around C counterclockwise plus you add up all the integrals around the little circles clockwise, and that will be 0. Bring this to the other side, you just change them by a minus sign, which is the same as instead of going clockwise, you go counterclockwise. So the integral of f along C is the sum over all these singular points of the integral of f along these circles, now going counterclockwise. But that's what I showed back here. That's just 2 pi I times the residue. So you get 2 pi I times the residue for each of those. And that's the proof of the residue theorem. With this notation as above, the line integral around C is gotten by adding up over all the singular points inside of 2 pi I times the residues. So it's like 2 pi I, this is 2 pi I times the sum of the residues inside C. That's the residue theorem. Now, if you want to use it, you have to be able to calculate those residues. And we're going to need to calculate these guys. So the author gives 3 scenarios. So the first one is, if you can fairly easily find the Laurent series, then you're in business. You just take the coefficient of the 1 over z minus z naught term. That's the B1. But that's not always an option. It's often very difficult or extremely difficult to find the Laurent series. But there's alternatives. Just sort of from knowing that the Laurent series exists, there's often alternatives. Suppose you know that f has a simple pole. Remember, that was a pole where that's a situation where the Laurent series looks like that. There's just one negative power, the negative 1 power. So you just set that one negative power, and then everything else is a power series. Now, you may not know these coefficients, but let's suppose you knew that it was a simple pole. Then you could find this coefficient as follows. Multiply both sides by z minus z naught. Then this side will become b1, and then a naught z minus z naught, a1 z minus z naught squared, and so on. All of these terms have at least 1 power of z minus z naught. So if you pass to the limit as z approaches z naught, they'll all go away to 0. And you'll be left with that. So you end up with this. Right? So to calculate b1, you just have to calculate this limit. Right? You may have been given f. You may know what f is, but you don't know its Laurent series. But if it's a simple pole, this is a way to find this coefficient. And it turns out that if this limit is not 0 infinity, then the pole is in fact simple, and this is the residue. I see, how could this be 0? This could be 0 if this wasn't even there. Because then what you would get, everything would have a power of z minus z naught. You would just get 0. But if this isn't there, then the function is actually analytic. And if the pole is higher degree, then there might be something with a z minus z naught squared. Then when you multiply by z minus z naught, you're not going to kill off that power. There'll still be a negative power, and the limit will be infinity. But the case where there actually is one negative term, and it's just the negative 1 power, that's the case where this limit will be bigger than 0 but less than infinity. And in fact, after the fact, you'll see that it was a simple pole, and this is in fact the residue. So for example, looked at sine of z over z squared. Find the residue at 0. Well, this one is easy to find the Laurent series, because we know the power series for sine z is that standard one. We divide by z squared, and it just gives you this. Here's the Laurent series for this function expanded in the vicinity of 0. And of course you see one negative power, so the residue is this coefficient 1. And notice if you took the limb, if you multiplied by z and took the limb, multiply this by z, you get sine z over z. And then, of course, we know that limit is 1. So that kind of verifies, the calculation. Either way, you end up with the residue. So that's there's a simple pole. Finally, what if the pole is higher order? Then it'll have a Laurent series something like this. So there'll be a bunch of negative coefficients, and the last one will be z minus z naught to the n. But we play the same kind of game we did over here. I want to clear these denominators, but I'm looking for this guy. But I want to get rid of all these terms. So I'm going to multiply by z minus z naught to the n. So multiply both sides by z minus z naught to the n. Then all of these terms, you see, will have a bunch of powers of z minus z naught. To get rid of them, I'm going to differentiate n minus 1 times. See, this one will have n minus 1 powers. The ones before it will have fewer than n minus 1 powers. So if I differentiate it n minus 1 times, I get 0. It's like if you differentiated this guy 3 times, it would become 0. So when you differentiate n minus 1 times, all of these are 0. And what about all these terms on the other side of this guy? Well, when you see they have at least n powers in them. So when you differentiate n minus 1 times, they'll be left with at least 1 power. The first one will have 1 power of z minus z naught. The next one will have 2, and then 3, and so on. So they'll have at least 1 power, and that'll go to 0 as z goes to z naught. Or what about this one? This is the one where if you differentiated n minus 1 times, you just get a constant. You get n minus 1 factorial times this number, right? Because it's like if you differentiate z cubed 3 times, you just get 3 times 2 times 1. So if you differentiate this n minus 1 times, you'll get n minus 1 factorial times b1. So again, what that means is I take the function, multiply by z minus z naught to the n, then I differentiate, so multiply by z minus z naught to the n, and then I differentiate it n minus 1 times. Again, that will make all of these terms be 0. This term will be n minus 1 factorial times b1, and all these terms will have at least 1 power of z minus z naught in them. So when you pass to the limb, they go away. And you're left with this one. Well, I just want the b1, so I divide by the n minus 1 factorial. So here's my formula for calculating the residue in the situation where we have a pole of order m. Here's an example. Look at z minus 2 over z squared 1 minus 2z squared. So you can sort of tell this as a pole of order 2 at the origin. Why? Well, look, it's 1 over z squared times this expression. But this expression is analytic at z equals 0. This has no problem with derivatives at z equals 0. So this expression would be given by a power series expanded in powers of z. And then when you multiply the power series by 1 over z squared, you end up with, your most negative power is the second power. So it's a pole of order 2. So what I do is I multiply this expression by z squared. That gets rid of that. Gives me that. Then I differentiate it 2 minus 1. I differentiate it once. Divide by 1 over 1 factorial. That's 1. And then I take the limit as z goes to 0. So I take this derivative. I do that here and take the lim as z goes to 0, and I get negative 7. So that's pretty much what you'll need to calculate all these residues. So very often they're just simple poles, and you might even be able to figure out the Laurent series because from sine or cosine or exponential or a geometric series, something where it's easy to write down series. And if you can write down the series, just pick out that coefficient of the B1 coefficient. But if it's inconvenient to write out the series, you do this. So if you think about it, this is really a special case of that, because here, if n was 1, that's the case of a simple pole. You'd multiply by z minus z naught to the 1, which is what we did, and you would take no derivatives, and you would divide by 1. So that's exactly what this is. So this is a special case of that when n is 1. But when n is 2, 3, 4, whatever, this is what you have to do. So it gets a little complicated because you have to take some derivatives, a number of derivatives. In examples we'll look at, the pole would generally be at order 1 or order 2, maybe at the most order 3, so we won't have to go too crazy in taking derivatives. So it shouldn't be that hard to calculate residues. Okay, so we're going to use all this in the next lecture. We're going to actually apply all this in calculating some good old-fashioned integrals. See you then.